Welcome back to Science Click. Today we'll explore a fascinating question. What would we see if we fell into a black hole? A black hole is a spherical region of the universe, a kind of space-time bubble with an immense gravitational pull. This bubble attracts objects almost as if pulling on the fabric of space, much like a star or planet. The surface of this bubble is called the event horizon, which divides the universe into two regions, the exterior and the interior. Beneath the horizon, the pull of gravity is so extreme that nothing, not even light, can escape. We know our universe contains many black holes. Although they are distant and pose no threat to us, one might wonder, out of curiosity, what it would look like to fall into one. Exploring this can deepen our understanding of extreme phenomena in the universe and correct common misconceptions. At the core of our galaxy, the Milky Way, lies a supermassive black hole called Sagittarius A*. For this thought experiment, imagine approaching it aboard a spaceship. After getting to a safe distance, you jump into the void of space, initiating a 1-hour fall that will ultimately be fatal. The spaceship remains in orbit, observing your descent. Before the fall begins, you face your first challenge. Sagittarius A* is supermassive, with a gravitational force equivalent to millions of times the Sun's mass. Its gravity captures surrounding stars and matter, forming a dense, plasma-filled disk orbiting at nearly the speed of light. This disk generates intense heat and radiates ultraviolet X-rays and gamma rays. Without protection, these would blind you and burn you alive. For the sake of our journey, let's assume you're equipped with an ultra-resistant spacesuit that shields you from heat and filters harmful radiation. Your helmet's visor adjusts brightness, allowing you to observe the disk and the stars beyond. Initially, you notice the disk appears blue. The visor filters all but visible light, and in this spectrum, the disk emits more blue light due to its higher energy, a phenomenon similar to the bluish tint of very hot stars. Curiously, one side of the disk looks brighter than the other. This is caused by the Doppler effect. The side of the disk moving toward you compresses light waves, making them appear brighter, while the side moving away stretches the waves, dimming them. Moreover, the black hole's gravity warps light, causing the back of the disk to appear folded around the horizon, creating a ring of light. Background stars also appear slightly blue due to the black hole's time-distorting effects. Interestingly, during the first 10 minutes of your fall, the black hole seems to shrink in your field of view. This happens because of a phenomenon called aberration. As you move toward the black hole, the light rays from it appear squashed towards the front, altering your perception. After these initial minutes, you accelerate to 4% of the speed of light, and the black hole starts to grow in your view. The Doppler effect intensifies the light in front while dimming the light behind you. Meanwhile, the spaceship's clock seems to tick slower due to the same effect. After 57 minutes, you pass the innermost stable orbit of the disk, where matter begins spiraling rapidly into the black hole. From this point on, things accelerate dramatically. 2 minutes later, you cross the photon sphere, a region where light can orbit the black hole. To the passengers on the spaceship, your image slows, fades, and freezes at the event horizon. For you, however, crossing the horizon feels uneventful. Light from distant stars still falls with you, and you can see both your body and the spaceship in orbit. Inside the black hole, local space-time appears normal to you, but globally, everything is drawn irreversibly inward. Surprisingly, the black hole's image occupies only 15% of your field of view, thanks to aberration, which contracts light ahead of you and expands it behind. However, after another 30 seconds, as you near the black hole's center, spaghettification occurs. The intense difference in gravitational pull stretches your body until it disintegrates. In your final moments, you perceive falling onto a flat black surface surrounded by a ring of light before your remnants reach the singularity. Currently, physics cannot describe what happens at the heart of a black hole. Our theories predict singularities, points where space-time curvature becomes infinite, but these are likely oversimplifications. Unifying gravity with quantum physics may one day solve these mysteries. Some theories suggest additional effects, such as multiple horizons or mathematical instabilities in rotating black holes. For now, our models provide insights into these cosmic giants and help dispel myths, like the belief that black hole disks are orange, they're actually blue in visible light, or that you'd witness the universe's history as you fall. These misconceptions overlook the effects of the Doppler effect and light aberration. Although mysteries remain, studying black holes brings us closer to understanding the extreme regions of our cosmos.